So we'll start with ellipses. Okay. Now I didn't make you memorize this formula, so I don't expect that you would have it memorized. But does anyone happen to remember the rectangular formula for an ellipse? It's been a while, I know.
X minus h or something squared over a.
A squared, okay, but you're on the right track, yeah, okay. And then what? Yeah.
There's another one that's like y minus b is in b or some other letter.
Yeah, some other letter, we'll call it k.
Squared over b.
B squared, yeah. And what do these always equal to?
0.
So usually these will equal 1.
Or 1.
Yeah. So very close, only 1 off.
Just subtract the other side and then
So just as a reminder, I know it's been a while. I don't expect you to remember every little detail about this formula. But when you have an ellipse, let's say the ellipse looks something like this. The center is HK. So that's what this HK represents. So that's the center of the ellipse. Then half of the major axis, or the distance between the center and the vertex, what constant is going to represent that distance?
on the major axis,
A. Yep. And then the distance between the center and the co-vertex, in other words, that shorter, that minor axis, that's B. Okay. So I'm going to go ahead and just give you the parametric equations up front. A little bit later, we'll kind of dig in to figure out like why those are what they are. But if you want to write an ellipse as a set of parametric equations, this is the formula right here. X equals h plus a cosine theta, and our y equation is going to be k plus b sine theta. So notice here that a, b, h, and k are still our coordinates, are still our the same variables that we have in the rectangular formula. They represent the exact same thing. The only difference here is theta. Theta is going to be our parameter. You know, most of the parametric equations we've looked at so far, the parameter we use t for time most of the time. But here we're going to use theta. Okay. So we're going to get into graphing these a little bit later, but first I want to show you algebraically how to go from the rectangular form to a set of parametric equations and vice versa. Because it's going to be a lot easier to graph these if they're in rectangular form, right? You can plot the center, you figure out your axes, and then you just connect the dots, right? After you find your vertices. So if they're written like this, it's not quite as obvious unless you know what all the pieces are. So anyway, let's first go from rectangular to parametric form. We're going to go the other way too, so I'm just going to give myself a little bit of room here. So if we're going from rectangular to parametric form, let's say I give you some equation in rectangular form like x plus 1 squared over 4 plus y minus 1 squared over 9 equals 1. So this is an ellipse. Right? The center is at negative 1, 1. The major axis is vertical because the larger number is underneath the y. And that major axis has a length of 6. This is a squared right here, so a would be 3. So like this distance, if I were to turn it like this would be 3, so the whole major axis would be 6. the minor axis would be 4. Okay, so let's convert this to a set of parametric equations. So this just requires a little bit of a trick here. Okay, the first thing is we are going to try to write this as a sum of squares. And it's almost set up for you already. You just have to make one little adjustment. And that is we want to write something squared plus something squared equals 1. Luckily, these two denominators are usually already squares. So doing this is not going to be that much of a challenge. Okay, so what I mean by that is I want to rewrite this as x plus 1 over something squared. So what would that something need to be? 2. Right. Plus y minus 1 over 3 squared equals 1. So I'm not changing the value of anything. I'm just simply rewriting it as a sum of squares. And the reason why I want to do that is because ultimately I want to know, or I want to find an equation for x and an equation for y in terms of theta. And we are going to use a Pythagorean identity to do that. So it's been a little while since, remember that proof unit from the first quarter? That was like unit 3, I think. But we're not going to use like all those proofs and all that. There's just one identity we're going to take advantage of, and that is, well, let me ask you this before I give it to you. Do you remember any of the identities? Like, is there one identity that you could, that's like you could think of?
Nope.
Nothing?
Like tangent equals 1 over cotangent.
Yeah, okay, so tangent is 1 over cotangent. That would be like one of the reciprocal identities, right? So you have like the reciprocal identities, you've got the quotient identities, and you've got the Pythagorean identities.
Plus or minus 1.
Y'all remember any of the Pythagorean identities? It's okay if you don't.
It's like sine squared plus 1 is equal to
Something like that, right? So I'll just go ahead and give it to you. It's okay. It's been like 6 months since we talked about it, right? So the Pythagorean identity we're going to take advantage of here is cosine squared theta plus sine squared theta equals 1. Okay? So we're going to basically make a substitution here, and the reason why we're allowed to do this is because, so I'm going to say since cosine squared theta plus sine squared theta is 1, if we know that this statement is true and this statement is true, then we can make a substitution here. Okay? Look at these two statements. Notice that both of them say that something squared plus something squared equals 1. Okay, so what we're allowed to do here is say we can let cosine of theta be this, x plus 1 over 2. And we can let sine theta equal this, y minus 1 over 3. So all of a sudden, we just got two separate equations, right? One referring to x and one referring to y. So the only thing left to do is just solve each of those two equations for x and y respectively. So like if I want to solve this top equation for x, what do I need to do? Like I want to isolate this x right here.
Multiply by 2.
Multiply by 2 and then do what?
subtract 1.
Subtract 1. So that would be negative 1 plus 2 cosine theta. So that's your x equation. Now let's find the y equation. To find y, or to isolate y, we need to multiply the 3 and then add 1. So 1 plus 3 times sine theta. So this is my set of parametric equations. Now, what kind of advantage does this give us? Well, if you're trying to say that like, oh, planet is orbiting the sun in an elliptical fashion, which they do. Why would you want to write it like this? Or like, what could the advantage be to writing it as a set of parametric equations versus a set of just a single rectangular equation? What extra information do you get?
You can figure out like where it would be on the ellipse based on what like angle it's making from where it started.
That's exactly right. But not only that, it also tells you which direction the planet's orbiting. Like, is it going clockwise or is it going counterclockwise? Okay. So we'll look into that. And really, the best way to figure that out is just to plug in values for theta, and then just figure out like what order they're being plotted in to see if they're going clockwise or counterclockwise. Any questions about going from rectangular to parametric? It really hinges on this identity right here. That's what we're going to take advantage of to do that. Now going backwards, we're going to take advantage of that same identity. And we're going to basically do these exact same steps but in reverse. So let me show you an example of going from parametric to rectangular. So let's say we have a set of equations like x equals 4 plus 3 cosine theta and y equals 1 plus 3 sine theta. And I'm trying to convert that to a rectangular equation. Okay, well, first, what I need to do is solve each of these equations for cosine theta and sine theta respectively. And the reason I want to do that is because if I can figure out what cosine theta equals and what sine theta equals, I can then plug it into this identity, which has to be true, to get my rectangular equation. So I'll start with the first equation. If I want to isolate cosine theta here, I need to subtract 4 and then divide by 3. So cosine of theta equals x minus 4 over 3. And so what would sine of theta equal?
Y minus 1 over 3.
Yeah, y minus 1 over 3.
This one a circle?
It may be. What indicates to you that it's a circle?
I just remember that the circles have like the same thing under the.
Yeah, exactly. You can kind of see what's happening. Like your A and your B are going to be equal here. And so if we think about an ellipse where the minor axis and the major axis are the same length, that's a circle, right? It's like having a rectangle that has 2 dimensions that are equal. You call that a square. So you could say like a circle is to an ellipse, a square is to a rectangle. It's the same kind of idea. But yeah, so this one is going to end up being a circle. It's still an ellipse, just like a square is still a rectangle, but it's exactly. It's a subset. Yeah, good. Okay, so now we can make our conversion. We're going to make this sort of the same statement. We're going to take advantage of this identity, cosine squared theta plus sine squared theta equals 1. We're going to substitute cosine theta for what it equals and do the same thing for sine theta. So cosine theta is x minus 4 over 3. Sine theta is y minus 1 over 3. And so to put it in sort of the proper format here, we want to actually square that denominator out so it looks like our normal template. So we get x minus 4 squared over 9 plus y minus 1 squared over 9 equals 1. So you can see how we can go back and forth. And again, both of these hinge on this Pythagorean identity. Any questions so far? All right, so that's all. that's all about ellipses. Let's talk about hyperbolas. So the rectangular equation for a hyperbola is almost exactly the same as an ellipse, right? But do you remember what the only difference was?
Adding the two terms or subtracting them.
Yeah, that instead of plus, you'll have minus, right? So, and this will be different if you have a vertical transverse axis, but if you have a horizontal transverse axis, and this is going to be true most of the time, you're going to have x minus h squared over a squared minus y minus k squared over b squared equals 1. So you see it's very similar. And just to kind of give you a quick picture of what we're graphing here, you have a center, you've got your vertices that are going to be equidistant from the center. You got some foci a little bit further out, right? At some point you'll have to draw these asymptotes, and your hyperbola will look something like this, right? Now, as far as all those parameters are concerned, hk is still the center, just like on the ellipse. Your a value will be the distance from the center to the vertex. And then the b value will be this distance right here. I don't know if you recall, but we graphed these using a little rectangle to help us find the slope of the asymptotes. And so that can help you sketch that out.